My name is Alexey Andreev. I'm a network engineer at Facebook. And I'm going to talk about next generation data center network, which we call Data Center Fabric. Nazem helped me a lot with the introduction of how we did things before. So let me do a quick overview of that. So before, we've been building our network in large units of deployments called 4-port clusters. 4-port cluster is built around 4 large cluster switches. It has a couple of hundred of racks underneath. And it's a layer 3 network all the way down to the racks. So the only routing protocol we run is BGP. The dots in the bottom are server racks. Each of them has a Tor switch in the top, so pretty much a basic topology. It's worth mentioning that this is a very large unit of deployment, as you can see. In our typical data centers, there are many clusters. On the front, they push traffic to the internet, to people who use our applications and services. On the back, they do talk to each other. And both types of communication grow. And as Nazem demonstrated, the growth rate is pretty much exponential, especially on the cluster-to-cluster communications. And clusters prove to be an inefficient way to scale specifically for that, for communications between them. Because there's a balance between how big is a cluster and how much uplink capacity it can have. So what we did to address it, we replaced this network of clusters with oversubscribed inter-cluster connectivity with one building-wide data center network. Each dot on this network in the bottom is the same rack with the servers and a top-of-rack switch in the top. It's pretty much the same building block. The colored dots are mid-size, simple infrastructure switches. They're different platforms available from various OEM vendors, or maybe just what you've seen a moment ago. But at the same time, for us, they are just colored dots on the diagram. They're just boxes on the network. There's nothing special about them. It's a very highly scalable network, and it's pretty high performance. Today, all inter-switch links are 40 gig, but it can scale beyond. It natively supports IPv4 and IPv6 as any networks that we do. It's again a layer 3 network, again based on a single routing protocol. And the important aspect is software driven. There are many ways to picture a fabric network. Like, for example, on this diagram, all 3 pictures represent exactly the same thing. It's just rearrangement of dots. At the same time, I can't really draw our network to its real scale. So this is purely visualizations at a very small scale. At our realistic scale, it becomes just a blur of lines. There's way too many links. So how does it work? A building block on our fabric is ServerPod, which is nothing special. It's like a microcluster. It's a layer 3 micro 4-post. It has 4 fabric switches in the top. It has 48 rack switches in the bottom. So it's 48 racks aggregated on 4 aggregation points. There's a lot of pods in the fabric, and they interconnect by parallel spine planes. That's the forwarding capacity between the pods. ServerPod is a much smaller unit of deployment than what a cluster was. Fabric offers many paths between the servers, and Fabric scales by adding the paths. We add spine devices, and the paths are added to contribute to this distributed forwarding performance. This diagram shows only 5 spines per plane, but in reality, there is many more. Again, I cannot draw the real thing. The paths appear to be different on this diagram, but this is purely like visual representation. They're equal performance paths. They're absolutely identical. So different flows on the network take these different paths and happily coexist on this large distributed environment. The network can survive multiple device failures, component failures, port failures, cable failures, with absolutely no impact. The individual devices and links are not important for us at all. So as Nazem said, if one fails, we can come next Tuesday to fix it. How's it better? One, it's a very modular system that allows us to scale in any dimension that we need to scale in. If we need to add compute capacity, we add server pods. If we need forwarding performance, we add spine switches on the planes. it's pretty much a very uniform and structured and predictable way for us to grow. We know what we add, and we can add in multiple dimensions. It offers much more bandwidth than what the cluster network offered us before, and it allows us to gradually grow into that full capacity. We can start small. We can start 4-to-1 rack-to-rack oversubscription, and what that means, we have 48 racks on the bottom, we have 12 spines per plane on the top. So for 48 inputs, we have 12 outputs, 4-to-1. Even this starting point is providing us 10 times more inter-building, inter-cluster communication bandwidth than what we had before with the oversubscribed cluster network. Then we can gradually grow. Let's say we can go to 2-to-1 by growing the spines to 24 switches. Or we can go to completely non-blocking network with the 48 switches per plane. It's also future-proof. To go even higher in capacity, we can upgrade link speeds. We can go 100 gig, we can go 200 gig, we can go 400 gig. We designed the topology to be able to support that, and we designed the environment to be able to scale to that too. Or we can increase the number of spine planes within the same port speed. If we go 8 planes, that automatically doubles the capacity. One important aspect we designed, even with this gradual initial start, we designed our physical infrastructure for the end state, including rack space, power, cooling, cabling. Everything is built to reach the end state. So we can gradually add the devices as we need. Let's say this is a sample spine plane up to the intended target capacity. And all the infrastructure, all the passive things are already in there. We can do it very quickly. One aspect that Fabric simplifies is sizing and capacity planning. Before, with large cluster switches, there's a constant balance of how big is the cluster versus how much uplinks it can have, what is the inter-cluster performance, and so on. If something changes, does it mean we have to take racks out of the cluster? This is really not something we can comfortably do because it's a lot of work, and it's a valuable resource. So we solved this problem by taking a small box, a mid-sized switch, and cutting it in half. For every port that is downlinked to a rack, we are foreseeing the same amount of capacity going out of this little device. And we just clone lots of these boxes and build a network out of them. Bigger does not necessarily mean better in our particular environment because, again, of these balancing problems. Then there are also problems going to the next port speeds does not happen as fast with the big radix form factors. Those speeds usually are introduced in the smaller form factors before they grow into larger systems. The bigger boxes also have proprietary architectures on the software and hardware side and require a lot of knowledge to operate. So and each platform is different. So one device versus another device is a completely different set of knowledge that you have to have. And they have a bigger blast radius as well if something goes wrong. So these small boxes are much simpler. They have very simple architectures inside. There are little fabrics inside these boxes typically based off pretty basic components. They're interchangeable. And they fail simpler. They simplify the operations a lot. But again, for us, they're just boxes on the fabric. And each individual box doesn't matter. One interesting effect, one interesting benefit of the fabric is optimization of power and cooling. Specifically power, like clusters were confined to particular contiguous physical space because of the cabling. They had to converge on these large cluster switches. And clusters have different power utilization profiles. Some are medium, some are high, some are low. But you cannot really swing the power from low power cluster side to the high power cluster side. You cannot just run a bunch of extension cords to the different side of the data center. This is not something that's going to fly. So in the higher power sides, we usually end up with some space that is not being used because there's no power for it, even if there is a power totally available in the room. With Fabric being built out of smaller pods, we can spread this utilization and intermix it in the whole data center evenly to achieve more even power distribution, better floor utilization, better power consumption in the data hall. We're finding many more benefits than bandwidth and scaling. For example, the uniform network underneath allows servers to have different roles depending on the time of the day. The life cycle becomes more granular. It becomes pod level instead of cluster level. The uplinks to backbone feature better bin packing, and there are many other things. On the flip side, Fabric Network brings some complexity too. There's a lot more devices and links in it, many more than what we had with the clusters, because there's whole spine tier and everything. There are some logical aspects of transitioning operationally from one platform to another platform. There are physical aspects. There's a lot of cables involved with the fabrics. There are scale handling issues with the networking gear. These basic switches need to be made to deal with this very large scale of routing that they are handling in this large data center. The routing protocol limitations, and the main thing, networks like this are simply not manageable by humans. Way too much complexity for a person to be able to troubleshoot it. So let's talk a little bit about the challenges, or more accurately, about how we address them and how we convert them to benefits. One perceived challenge is cabling. That's how the cabling looked in the data hall before. So a rack went to 4 aggregation points by uplinks. There were 10 gig uplinks. With Fabric, instead of cluster switches in the same aggregation points, we have Fabric switches now of the pods, and the cables became 40 gig. So it's essentially very little change inside the data hall. The same topology, same simplicity, and it's backward-forward compatible design. That crazy web of interconnects inside the spine is actually not that crazy. Even though its scale is hundreds of thousands of fiber strands, they're aggregated in large fiber trunks that are pretty much straight line runs from the position where the Fabric switches sit to the position where the spine switches sit. We put spine switches in special rooms in the center of our data center called BDFs, and the links from the Fabric switches to the spine switches, basic trunks. It's simple fat pipe going from one point to another point. They're equal length, they're independent failure domains. All complexity, all that weaving the fabric is contained in the BDF. And there it's very manageable. To help manage that complexity, we fully automated port map generation and we fully automated cabling verification. So our tools validate whether the devices are cabled correctly and suggest what changes need to be made to match the intended port map. This has proven to be very successful. We have less than 1% of the cabling errors in our very first deployments, and very quick resolution of problems whenever they happen. We also reconsidered our data center design to optimize it for the network. Before, the fiber plant was pretty complex and there were dependencies on the construction sequence. Now, we build data center from the center. We put the Fabric spine planes in the center of the building in those BDF rooms, and we deploy them very early in the building construction process. Then as the data halls get constructed, they are connected to the center by straight line trunks. This optimizes fiber distances, this improves the redundancy, and there is very simple fiber cabling as well, because there's just two fiber lengths, right? Nearest data hole, farther data hole for us. It's very simple. On the logical side, well, pod is a new beautiful unit on the Fabric, and they're all equal, which is a great benefit from the infrastructure management standpoint, but other teams are using clusters in a broader definition than just network. Even though the cluster definition was born as a limitation of like how much compute capacity we can consolidate on one large switch, it evolved into something much more. It's a capacity unit for many other people than just network engineers. So we needed to make the transition transparent for them, but pod is a way too small unit. They didn't work with this many microclusters before. They need their like approximately same unit of capacity. So we made it very simple. We named a collection of pods of the clusters, and that allowed us to approximate the existing cluster sizes very well. This also added flexibility in the cluster sizing. We can start as small as single pod or make the whole building a cluster. It's a collection of pods in either case. So the pods can be deployed gradually, which means the provisioning and decom lifecycle can be more granular in such clusters. The other advantage, they don't have to be sequential anymore. We can intermix them, and they can even span different physical rooms, wherever the space is to continue growth of a given cluster. At the same time, to preserve this compatibility with our previous cluster model, we maintained all the same logical sequencing, naming, addressing, and numbering within them as the were real clusters. So we call these virtual clusters. They look to our server management systems, to our other non-networking automation systems, the same as our old clusters looked before, but they're implemented on the fabric. Let's look at it another way. Like, this is an imaginary data center with physical clusters in it. Each cluster is a large unit encircled in its own dedicated high-performance network, this little blue cloud. But the links between these networks are heavily oversubscribed and quite weak, and they're not scaling for our inter-cluster communication needs. What we did, we replaced these dedicated networks with one uniform wall-to-wall network in the building, which is a utility. It became the same thing that is present in every rack as power, cooling, physical space, and network. It's the same in any spot of it. But we kept the clusters the same, opening up the possibility for them to evolve. Like, by using more pods, clusters can become bigger. Cluster can span suites. Eventually, we can evolve to a definition of data center being a cluster, or we can go with just pods. We have the flexibility to do it. On the technology side, we spent a few months in the labs to play with different topologies, different platforms, different protocols and technologies. Fabric poses quite a few interesting challenges. We just went ahead and redistributed everything to flood everywhere on the fabric. There would have been like hundreds of thousands of prefixes per address family. This is not associated with small and simple devices. But we were able to minimize the fib and rib utilization by BGP design and minimize control plane loads to make it really suitable for the small and simple devices. And this fabric complexity is not always translating into the logical. Like, we were able to simplify things. Like, for example, that was our old BGP policy on the rack switch, and our new became much simpler with the fabric. We take advantage of the distributed control plane for convergence performance and for scalability. BGP is a protocol built to scale. At the same time, we have means to override the default behaviors by centralized controller. We have a BGP controller that can customize any path on the network by injecting specific paths across large parks of devices. We can program paths hop by hop to customize whatever flows, if the default doesn't work for us anyhow. But we are finding that with our very large number of flows, ECMP is almost ideally even on the network by default. So the most time the controller spends is in monitoring mode. It watches the BGP tables on the boxes, looks for inconsistencies, isolates faults, but does not actually intervene for the most of the time. This network is not manageable by humans, so let's take a look of how we made it manageable by automation. First part is config generation. Of course, the configurations for the device is automatically generated on this network, but we're not actually grabbing a device template and filling it with a bunch of parameters. That's way too many templates and way too many parameters. We start on much higher level. Our input parameters for config generation are high-level things like form factor, like what is the size of this fabric, how many planes it has, and things like this. Parent IP spaces, virtual cluster definitions, vendor abstracted routing policy definitions, purely the logic of routing of the network. Some syntax translators, like how do we configure a BGP community on a platform X, or how do we configure an interface or a route, or things like this. And various regex-driven definitions that cover wide ranges of devices at once, not device by device. So we can cover, by very flexible regex, properties of whole parks of devices. On the output goes all the granularity, the objects in the database, the configurations in the repos, all the individual port maps, even dashboards are outputs of the fabric config. So again, the main differentiator, we're not working with device configs anymore. Device config is a derived element. We're working with the whole fabric config. And the other thing, we are doing this the same way as we are working with our code. So all the inputs and outputs go through the same diff review process as what we used for our programs, which is very commonly used in this environment and ensures integrity. To simplify deployment, we made our systems auto-discover and auto-provision the boxes connected to the network. Whenever a new box connects to the network, our system come in and try to understand what this box is based on its peers. If everything is cool, if the health check passes, if the box corresponds to the connectivity, it goes ahead and builds the box. It builds the box in a passive state. The box is not taking state. So the only thing left for the operator to do is to approve putting this box under traffic. And all the audits, all the health checks are already done, the box is warmed up and ready to go. This allows us to deploy many boxes in parallel at a very fast speed. Like literally this week, we are doing a large deployment of Fabric in one of our existing locations. And it started on Monday. By yesterday, 2 people already put in production over 120 boxes. Like they're fully running, fully cabled, ready to go, plugged into the systems on the network. Our requirements for the box are very simple as well. The box just needs to do some basics. It needs to support Ethernet. It needs to have some decent TCP/IP stack. It needs to do IPv6 and support like some very basic industry standard network protocols. On the routing, it's just BGP, and the feature set we on purpose keep very small. Then we need to know how to collect the data, how to push the data from the box, how to check the health of the box, like very basic operations, and those syntax translations. How do we configure an interface? How do we configure a BGP peer and things like this? Then we define a few very simple actions for these boxes, which are easy to implement on any platform. We define how to validate the state of the box, how to check the health, how to gracefully put it in service and out of service, how to clear configuration and apply a new configuration. These minimalistic requirements ensure broad compatibility. We deploy the boxes using a concept of hammer. It gets a box, it gets a config, it hammers it in. Everything in Fabric is deployed automatically with this simple workflow. And it's implementable across many platforms. We take it out of service, we destroy the current configuration, we apply new configuration, doesn't matter what complexity it is. We don't go into the what we call scalpel approach when we need to know like what command needs to go before what command, like what needs to be predefined before able to go to next step. No, we just apply the whole thing from scratch. Then we audit the box and we put it back in traffic gracefully, proceed to the next box. We have a system, we have developed a system that allows us to orchestrate these changes across large part of devices as well. Doesn't matter what the change is, whether it's a software upgrade, whether it's a broad config change, it's the same hammer mechanism. And we just launched our Altoona Fabric back in November, right? Since then, we rebuilt the whole network 4 times, including pushing new software images, including a complete overhaul of the BGP routing policy. By this mechanism. It was a hitless operation, nobody noticed. Configuration monitoring, for every config that we hammer in, we take a golden image of it and store it in the repository. So if there is a manual change, we get an alert in a diff of what it was before, what it is after. Then we have multiple options. We can either restore it to the original golden config, or we can work in this logic into the golden config templates. On the monitoring, we look holistically on the whole network. We monitor the weather. We don't monitor individual devices. It's way too many devices to concentrate on each single one of them. So if there is a hotspot, we see what it is. We see what's wrong with it. We can drill down. We can go troubleshoot. We do collect a wide amount of parameters across all the devices, but we don't look on them individually. There's no NOC monitoring them. We are looking on parameters across broad infrastructure elements and comparing the behaviors. And this information is mostly there for drill downs. So we can drill down into any data point at any moment of time when we need to. But it's not that something that we have to pay attention all the time. It's an investigation tool. For many of the problems, if something happens on the box, a robot comes in first and assesses what exactly is going on there. If it knows how to fix it, it fixes it. If it doesn't know, it escalates to a human to develop a fix. At Facebook, we are running one of the largest server parks in the world, and we're pretty good at that. We know how to manage them. Our switch park is growing as well, and we actually want to manage them the same way we do with the servers. They are essentially the same thing. The switch is a Linux box. We just had a little more ports and some hardware that supports line rate forwarding, and it runs a couple of custom applications, one to participate in the routing decisions, another to program that hardware. Otherwise, it's a Linux box. It's a server. It was a lot of fun to develop the networking aspects of the Fabric. This YDCMP and Scale presented a bunch of network engineering puzzles to solve, and they were very exciting. But what actually made it a production environment is tooling and integration into the Facebook automation ecosystem. As Najm said, there's not much new about folded multi-stage flow topologies. They've been around for a while. However, at this scale, there is not so many places in the world that such a large-scale flow has been deployed. There have been some other large internet services, there have been some supercomputing centers, but that's pretty much it. What we did with our automation, we enabled mass production of these fabrics as our mainstream infrastructure. Since launching our Altoona data center on the first fabric back in November, we already developed yet another one and launched in our other existing location. And as I said, we're building yet another one pretty much these days. At the same time, as we say here at Facebook, our work here is only 1% complete. There's always more exciting things to do. There's never enough tooling. In the end, it's all about the tools. The networks like this are simply not manageable by humans. Thank you. Yep. Please check out our blog post. It has more information about Fabric and other exciting things we have going on here. Thanks.
So I think we've got time for a couple of questions here. Please, if you have questions, there's the mics at the center and at the side. You've got, or we can walk around the mics.
Jonathan Cheng from Delta Networks. I just want to find out what is the target time frame for putting the 6-pack on OCP?
It's a matter of months, not necessarily more than that. As I said, we're in sort of early stage of testing, and we have a few boxes in production. As we get more comfortable with that it's working, then we'll sort of release it. Because you don't want to release it too early and then find problems and then have the industry react to it. So we want to get a little more time, a few more boxes in production, get more comfortable with our stability, and then we'll go from there. So it really just depends on how well the box behaves over time.
Hi, this is Vittal from Dell Networking. So I have a hardware question. So you talked about 100 gig, 200 gig, 400 gig Ethernet. As you know, there's no 200 gig Ethernet.
Right.
There's 100 gig and there's 400 gig being talked about.
Yeah. So.
So what are you guys thinking as far as 200 gig goes? And perhaps a follow-up question on that. You talk about the scalability of 6-pack from 100 gig to from 40 gig to 100 gig.
Mm-hmm.
Have you thought about beyond one generation? Because that requires, you have a backplane back there.
Yes.
That can support maybe 100 gig. We don't know what 400 gig looks like. So is it one generation? Is it multiple generations?
So I'll start with the easy one, which is the second one. So in the 6-pack, we have a built-in dual upgrade path. One is we're running right now all of our channels on the back at 10 gig. We have a 2.5x increase in bandwidth path just by running 25. The backplanes have been designed for 25, so they are ready for 25. The backplane connectors are 25. Everything is set over there. So that's our first 2.5x. We also provision the backplane with utilizing only 50% of the channels right now. So we can have another 2x step in there by utilizing the other 50% of the channels are basically doing the 2.5x plus 2x, basically 5x we can do just out of the bat. That's where the 200 gig comes from, the 45x. Now there's no 200 gig E, but 200 gig, we look at this as a pipe. It can be built out of 2 by 100. It can be built by a single 200. Like Najm was talking about, we're doing a lot of effort on the optical side, and we're stepping from 40 to 100. And in that effort to work into a single mode duplex solution in our optical side, we might have an intermediate step to create a wider pipe with 200 gig instead of 100. And we'll be able to leverage that pipe into the box when it's folded in through the backplane. Beyond 200 gig per port, we'll have to do things in a little bit more creative ways, like running PAM4s or all kind of other things that will do that.
Right.
Sounds good?
So what about 200 gig Ethernet?
So 200 gig E, we're not driving 200 gig E as a standard, but we see 200 gig as a pipe for us, an intermediate step pipe between 100 and 400. We feel that from 100 to 400 as a standard, it's going to take a while. And for us, we have to step much faster than that. If you saw our cycle, it's an 8 to 12 month cycle. Then we might have to take an intermediate step of 200. It's not going to be probably called 200 gig E, but still going to have a 200 gig pipe capability.
Thank you.
Could you describe Facebook's approach to network security?
I think in the interest of time, maybe we can take that one sort of
It's a
offline
broad-
and
it's a
sort of
broad
do a
question.
one-on-one conversation. It's a pretty broad
Yeah.
question. We're a little bit tight on time. So see me afterwards and we can talk about that.
So obviously a number of benefits that Facebook's getting from this solution, some of which would be shared by many other large companies operating at scale. And I was curious kind of what your view is on kind of the multi-billion-dollar enterprise switching market and what an announcement like this might.
You want to take that? You want me to take that? Okay, I'll start. The intent is not to go after any market or any individual vendor per se. What we're after is change the paradigm a little bit on how network devices or network technology is built, and move away from the monolithic or vertically integrated boxes or appliances, if you will, and disaggregate the component, invite the community to be able to actually develop a lot of technology and be able to leverage technologies being developed by several different companies, right? So we're after a different paradigm, not necessarily after a specific vendor or specific industry per se. I think the opportunity and the challenge that the vendors have in this space is to actually build components and build parts of this type of system and that are attractive enough for everybody else to buy. Because our philosophy always is that we don't necessarily want to build it until we think we really need to build it. So if there was a component available that we could just buy and it worked well for us, we would just go buy it. But if we can't, then we'll just go build it. We're not shy about either one. So the opportunity for the industry is to essentially step in and build parts of these components, and that stuff is already happening. We're seeing a lot of vendors sort of step in and talk about what they want to build or what parts they want to build. So as they said, it's overall an ecosystem change that we're looking for. Because we just believe in the open model a lot more. We believe in software control, and at our scale, which I think most everybody will get to eventually, is you need to be able to have some level of software autonomy. The configuration or CLI and protocol, that tool set just doesn't work anymore, right? So we need better toolkit, more ability to do stuff. So that's sort of what we're trying to do.
Very good. Thank you, and congratulations to everybody that was involved with this. It's
Thank you.
Amazing.
Thanks.
Hi, Steve Kotowski with Source Photonics. You mentioned earlier about the fiber component and how you wanted the same fiber to be working on 40 gig and 100 gig. And that has an impact on the optics. It also has a question of what are the distances you have to reach in the data center and what percentage are, 2 kilometer versus 3 meter or so forth.
I think I'll repeat Yuval's line that he said at last OFC. What we'd like to see is single mode fiber, 2 kilometers or less at $1 a gig for 100 gig, right? Yep. That's sort of what we would like. I mean, kidding aside, ideally, he wasn't kidding. He wanted that. 2 kilometers and below would be perfect. There are technology challenges that you have a sort of demarc at the 300 to 500 meters and above type environment. So ideally, if we can get a solution that works for 2 kilometers and below and 2 and above, that works perfectly for us. But in cases, you could think about a 90-10 sort of rule where 90% of the data center easily fits within the 300 to 500 meters sort of range, right? We can make that fit. And then 10% you go by a slightly different solution. That's still workable.
So the high cost, I would think, would be the optical module, and going from 500 meters to 2 kilometers would be a step in pricing. Mm-hmm. And maybe you'd want to reuse the fiber, have the same fiber solution for both.
Correct. The fiber plant itself, especially in an architecture like this, which is interconnect heavy, the fiber plant itself costs a significant amount of money. And if we had to replace that, and so if we deployed multi-mode for 40 gigs and then we had to do single mode for 100 gigs, that would be pretty expensive. Plus, it takes a lot of time to rip out fiber and put new fiber in the trays.
Right.
That's expensive. Time is pretty expensive. So we optimize for time. So ideally, if you can just replace the modules at the end and use the same fiber, that's what we're after. But we want to do it so that we can get to 400 gigs as well, because that's sort of the life of the data center itself, because data center buildings are 20-year depreciation cycles.
Okay, great, thank you.
Maybe last question? We can go.
You want to work? Yeah.
Go for it.
All right. So that was a great insight and sharing about data center network design. I was so excited about it. But how about data center design? Can we apply the same concept into that part as well, or do you have another exciting information to share?
Well, can you hear me? We actually typically do have multiple buildings on the data center site, and we have been running fabrics between those for a while. So it's the same topology, same architecture applicable between the buildings on our campus.
So that can apply to, let's say, data center here in the West Coast and a data center in the East Coast?
That would be backbone connectivity, and we have.
So, I mean, this time around, we decided not to sort of touch too much on the backbone side, just couldn't fit that much on the agenda. We didn't want to hog up all the time with Facebook stuff. So hopefully next time we'll talk a little bit more about backbone. There's a lot of work going on in that space as well. We're doing some trials in that space, and so hopefully in the future, some event will focus more on the backbone technologies. But I mean, you have to build optical networks, and there's really no other option. How you optimize the routing and traffic engineering layer on top of it is the more interesting conversation there.
Just one thing to add to that is, like we discussed, the 6-pack is built in Ethernet only on the back and whatever you want on the front. So you can imagine what things we can build on the front side of it.
Thank you.
All right, so I think we'll go on to lunch here. Just from a logistics standpoint, only this door is going to be open to get everybody through lunch, right? So we're going to have our own sort of network buffer queuing problem here, but that door is going to be open for lunch. If anyone here wants to come hang out with Yuval and the rest of the team here here's the 6-pack and actually a wedge up here, if you want to hang out here. And then we'll reconvene at 2 o'clock. We've got a whole bunch of other talks planned for the afternoon. So we'll see you in a little bit. Thanks.
From you.